I want you to just, for a second, picture the absolute worst traffic jam you have ever been in. I'm talking bumper to bumper, not moving for like an hour.
Oh, that's a painful memory for anyone. Just total gridlock.
Right. And you're sitting there, and the logic is simple. If you add more cars to this mess, things get worse.
Of course. Density equals slowness. The road is full. Nobody moves. That's just, physics.
But what if? What if that was completely wrong? Imagine that the moment the traffic got so bad that every single car was locked in place, you suddenly started moving 1,000 times faster.
It sounds impossible. I mean, it violates every intuitive rule we have.
It's like something out of a comic book.
Yeah.
The Flash enters flash time. The whole world freezes. Everyone's a statue. But he's just zipping around.
Uh-huh.
Well, get this. Scientists have just found a quantum version of that. They made a traffic jam of electrons so dense that the background froze solid, and somehow energy started moving at just record-breaking speeds.
It's an incredible discovery. It really flips the script on what we think of as an obstacle versus what we think of as a highway.
Welcome to the Deep Dive Lab.
Yeah.
Today we are digging into a paper that, honestly, it blew my mind. It's from the journal Science, published January 1st, 2026.
The paper is Giant Enhancement of Exciton Diffusion Near an Electronic Mott Insulator. It's from a team led by Pranshu Upadhyay and Daniel Suarez-Forero at the University of Maryland, along with others.
And we are going to shrink down to the atomic level to watch a quantum dance that, let's just say it breaks the rules of monogamy.
That's one way of putting it, yes. It's a fascinating look at quantum exchange interactions.
Okay, so let's set the stage. Before we get to the speed and the scandal, what is this material? What's the playground they built?
Right, so this isn't your standard silicon. They're using something called a heterostructure, specifically two different materials called transition metal dichalcogenides, or TMDs for short.
TMDs. I feel like I hear about these all the time now in material science.
Oh, they're huge. In this case, it's tungsten diselenide and tungsten disulfide, WSe₂ and WS2. And the key is that these are 2D materials.
So like one atom thick, like a sheet of graphene.
Exactly. And what they do is stack one on top of the other, but, and this is the critical part, they twist one layer just a tiny bit relative to the other.
Okay, I think I can picture that. It's like if you take two pieces of screen door mesh and lay one on top of the other, you get that weird kind of wavy psychedelic pattern.
That's the perfect analogy. That pattern is called a Moiré pattern. And for the particles living inside, that pattern creates a new, much larger energy landscape, a superlattice.
So instead of a flat surface, the electrons are living on, what, like an egg crate?
An egg crate is a great way to think about it, yeah. And into this egg crate, we put our players. First, you have the electrons. They're the background crowd, the cars in our traffic jam. We call them fermions.
Okay, so fermions are the obstacles.
Got it. And then we have our main character, the thing we're actually watching. It's called an exciton.
The exciton, right. Now, this isn't a simple particle. It's a quasi-particle.
It's a bound pair. So when a laser hits the material, it can kick an electron out of its spot, leaving behind an empty space, a hole.
A hole.
Exactly. And that hole acts like it has a positive charge. So the negative electron and the positive hole, they attract each other. They get bound together.
So they're like a pair of ice skaters holding hands.
Uh-huh.
Or, okay, for the Star Wars fans, it's a force dyad, like Rey and Kylo Ren. Two parts, locked together, moving as one.
A bound state, yes. And because it's a pair, it acts like a different kind of particle called a boson. And this is important. Bosons can sort of overlap and share space in a way that our background electrons, the fermions, cannot.
Right, the Pauli exclusion principle. Fermions are antisocial. They need their personal space.
In a manner of speaking, yes. So the whole experiment is about seeing how fast this exciton or force dyad can run across this Moiré egg crate.
Okay, so the team, Upadhyay and company, they start doping the material. They're adding electrons.
They're increasing what's called the filling factor, just adding more and more electrons into those little valleys of the egg crate.
So they're filling the room with people, adding cars to the highway.
Precisely. And at first, physics behaves exactly as you'd expect. Things get slow.
This is that polaron phase they talk about in the paper, right? What's happening?
It's all about interactions. The exciton has that positive hole, and the background electrons are negative. So they're attracted to the hole. They start to crowd around it.
So our exciton is trying to run, but all these other electrons are like clinging to it.
Yes, it gets dressed by the environment. It's dragging this cloud of other particles and distortions with it.
It's like trying to run through the swamp of sadness from the never-ending story. You're just getting bogged down.
We call that a polaron. And the paper's data is crystal clear. The diffusion, the speed, it just drops. It becomes a slog.
Okay, so far, so normal. More people, more friction, slower movement. Makes sense. But they didn't stop there. They kept adding more electrons.
They kept turning the dial until they hit a magic number. Filling factor 1.
Filling factor 1. In terms of our egg crate, what does that mean?
It means there is exactly 1 electron in every single seat. Every valley in the Moiré landscape is now occupied.
So it's like musical chairs, but everyone gets a seat at the exact same time.
And because they're all negatively charged, they're all repelling each other. And because they're fermions, they can't share a seat. They are locked, pinned in place by their neighbors.
This is the ultimate traffic jam, the gridlock.
It's a state of matter called a Mott insulator. The material should be a conductor, but the electrons are so jammed up they can't move. So it's an insulator.
So the background is frozen solid, a time-freeze spell. Logically, our exciton should be completely stuck now too, right? I mean, how do you move through a solid wall of statues?
That is what every textbook would tell you. The probe should be frozen. But that's not what they saw.
What happened?
When they measured the exciton's movement at that exact point, the speed didn't just recover, it skyrocketed.
Skyrocketed, as in...
As in 3 orders of magnitude faster. It started moving 1,000 times faster than it did when the material was completely empty.
Wait, hold on. The traffic is bumper to bumper, totally frozen. And our runner suddenly turns into Quicksilver from the X-Men movies.
That's essentially what happened, yes. In the middle of the densest possible traffic jam, the exciton becomes hypermobile.
That is just wild. How is that even possible? This gets to the why, and you mentioned something about non-monogamy.
Right. The paper calls it an exchange-driven transport mechanism, but non-monogamous really helps to picture what's going on.
Okay, let's break it down. Scenario A. Normal, slow movement. The exciton is a couple, electron and hole, holding hands. How do they move?
They move together, physically. The pair has to hop from one spot to the next.
Like a 3-legged race?
A 3-legged race, exactly. And if the room is crowded, like in that polaron phase, it's really hard to coordinate that jump. You bump into everyone.
Okay, that's monogamous motion. You stick with your partner, and it slows you down. Now, take us to the Mott insulator, the frozen grid. What changes?
The frozen grid is the key. The hole, the positive part of our exciton, has a revelation. It realizes it doesn't need to be loyal to its original electron partner.
Why not?
Because there's a perfectly good electron sitting right next door. And one next to that, and one next to that. In quantum mechanics, all electrons are identical, indistinguishable.
So it swaps partners.
Exactly. Instead of dragging its original partner through the crowd, the hole hops to the next electron in the grid. It forms a temporary exciton, then immediately dumps that electron and hops to the next one.
So it's not in a 3-legged race anymore. It's just trading partners at every single step. Hello, new partner, goodbye. Hello, new partner, goodbye.
It's propagating the idea of the exciton, the energy, without having to physically drag the same matter along with it.
That's crowd surfing. Think about it. You can't crowd surf if the crowd is sparse or moving around randomly. You fall right through.
You need density and rigidity.
Yes. You need the crowd to be packed shoulder to shoulder, locked in place. The fact that the electrons are frozen in the Mott state creates the perfect, rigid support structure for the hole to just fly across the top.
That's an excellent physical analogy. The Mott insulator provides that rigid, ordered lattice. It allows the hole to surf or exchange with almost zero resistance.
So the hole is just swiping right on every electron it passes.
Non-monogamous recombination, yes. And there's another part to it. The paper points out that the effective potential, which is kind of like the hill the particle has to climb to move, also gets much flatter.
Flatter how?
Because the electrons are arranged in such a perfect ordered grid, they screen the electrical landscape really effectively. It has the effect of making the exciton's mass drop. It becomes light as a feather.
So it's a double whammy. You get
Yeah.
to stop dragging your partner around, and the hills in front of you get flattened out. No wonder it's 1,000 times faster.
That's the mechanism. It turns the gridlock into a superhighway.
I love that. So this only happens at that perfect filling factor 1.
No. And this is where it gets even cooler. They also saw these speed spikes at what are called generalized Wigner crystals.
Generalized Wigner crystals. Okay, that sounds like something out of Star Trek. Captain, we're detecting a Wigner crystal formation.
It sounds like sci-fi, but it's a very real state of matter. It happens at fractional fillings, like when the egg crate is only 1/3 full or 2/3 full.
So when the room is mostly empty.
Exactly. But the electrons don't sit randomly. They repel each other, remember? So to get as far apart as possible, they arrange themselves into a new, perfect, repeating crystal structure, a triangle pattern in this case.
So they form a crystal out of empty space, essentially.
They do. And what the researchers found is that whenever that geometric order appeared, whether it was the full Mott state or these fractional Wigner crystals, the Exciton diffusion shot up.
That's the smoking gun. It's not just about density, it's about order.
That's the key takeaway. If the crowd is messy and random, the exciton gets stuck. If the crowd is ordered and crystalline, the exciton can surf.
It's like the excitant can read the room. If it sees a pattern, it can fly. If it sees a meth, it gets bogged down.
And this effect is surprisingly tough. They found it works up to about 200 Kelvin.
200 Kelvin is, what, minus 100 Fahrenheit? So it's cold. But for this kind of quantum stuff, that's practically a beach party.
It's very hot for these kinds of correlations, yes. Usually these delicate states just melt away from heat vibrations, but this mechanism is robust.
So let's zoom out. Why should you, listening at home, care about this? I mean, we're not building a quantum superhighway on the 405.
I know, but this has huge implications. First, it's a new way to move information. Right now, all our tech is based on moving electrons moving charge. That generates heat and resistance.
Right.
If we can move information using these excitons, these packets of energy, in this kind of resistance-free state, it could lead to much faster, much more efficient devices.
So excitonics instead of electronics.
Potentially. But even more immediately, it's an incredible new sensor.
Sensor. How?
Well, we just established that the exciton speed is super sensitive to the order of the electrons in the background.
Yeah, it zooms on a crystal, it crawls in a mess.
So you can use it as a probe, you shine a light on a material, create some excitons, and just watch how fast they spread out. Their speed tells you exactly what the invisible electrons inside are doing.
So you can use the excitant as a spy to see these hidden quantum states.
Precisely. We can see these Wigner crystals or magnetic ordering without ever having to touch the material with a wire. It's a powerful new tool for our quantum toolbox.
That is truly mind-bending. Okay, so to bring this all home, what are the key takeaways?
I'd say 3 things. 1, we stacked 2D materials to make this Moiré playground. 2, we jammed it full of electrons until they froze into a Mott insulator, a perfect gridlock.
And 3, our hero, the excitant, instead of getting stuck, just started crowd surfing. It used quantum non-monogamy to hop across the frozen electrons, moving 1,000 times faster than it ever could in an empty room.
A perfect summary. It's the triumph of collective order.
You know, this completely changes how I'm going to feel next time I'm stuck in traffic.
Oh, yeah.
Yeah. I'm not going to get frustrated. I'm just going to wish I could decouple from my car, act like a quantum hole, and just surf right over the top of everyone.
I'd probably advise against trying that in practice, unless the cars are in a perfect crystal lattice.
Duly noted. But it does leave you with a fascinating thought. We always think that freedom, empty space, is what you need for speed.
That obstacles are inherently bad.
Right. But here, the obstacles, the jammed up electrons, they became the bridge. The rigidity of the system is what created the superhighway. So here's our final thought for you to chew on. If a total gridlock can create the perfect conditions for speed in the quantum world, what other bad conditions in our world might actually be the secret to a breakthrough? Where else are we trying to clear the path when maybe we should be trying to organize the obstacles?
That's a deep one. Sometimes a solid foundation is what you really need to fly.
Exactly. Thank you so much for joining us in the Deep Dive Lab. If you enjoyed this trip down to the atomic scale, make sure to hit that subscribe button. We've got a lot more to explore.
Thanks for listening.
We'll see you next time.